Two main approaches to pruning exist. The first approach, probably the simplest, is called reducing error and consists in removing branches from the fully grown tree. In order to determine the optimal subtree, the prediction error of each of the subtrees is computed on an additional dataset called the validation dataset. The procedure then consists in choosing the subtree with the smallest error on the validation dataset. This method is cheap in computation time, but it requires to have an additional dataset available, which is not used to build the tree, but to adjust its complexity. Usually, the dataset is split into a training set and a validation set, which has the consequence of reducing the amount of data available to train the tree. The second approach, called cost complexity pruning, is based on penalizing the error of the decision tree by the number of leaves it contains. Let's detail this approach. Let us imagine that the decision tree has already been constructed, and let us denote it by T0. For any tree T, let RT be the risk of this tree, equal to the error rate, the percentage of bad predictions in classification, or its quadratic risk in regression. This quantity can also be written as the impurity of each leaf of the tree, weighted by the proportion of observations in each leaf, if the impurity measure chosen is respectively the error rate in classification or the variance in regression. Note here that the error rate as an impurity appears again. The error rate should not be used to build the tree, but is commonly used during the pruning step. The risk of the fully grown tree T0 is 0. Indeed, each leaf of this tree is pure, so its impurity is 0. The error of this tree on the training set is thus 0. However, as we have seen, the training risk does not reflect the prediction performance of the tree on a new dataset. Let us define for any positive alpha a cost complexity measure that we write R alpha t for each tree T. This measure is a sum of two terms, the first one being the risk of the tree T computed on the training set, in other words RT, and the second one being a penalty term involving the parameter alpha and the number of leaves of the tree T. This measure R alpha t is a penalized version of the risk RT. We add to the risk RT a positive quantity, increasing with the complexity of the method. Indeed, the complexity of a tree increases with its number of leaves. Let's take the simplest tree. It is the root of the tree, in other words, a tree containing no splits. Its risk, RT, is thus equal to the impurity of the root. Its penalized risk is thus equal to the impurity of the root plus alpha. In this case, it is likely that the risk of the root is large compared to alpha, i.e. that the dominant term in the penalized risk is the risk of the tree. Conversely, if you consider T0 a very complex tree because it is completely developed, its risk RT is 0, but its number of leaves is high, equal to n, the number of observations. The dominant term in the penalized risk is therefore the second term called the penalty term, which equals to alpha times n. The penalized risk thus takes into account both the predictivity of the method and its complexity. For each value of alpha, we can minimize the penalized risk and obtain an optimal tree T star alpha. Finally, the parameter alpha can be chosen by cross-validation to lead to the optimal prune tree T star.